So welcome to the fourth annual Distinguished Lecture of the Natural Philosophy Forum here at Johns Hopkins. The Natural Philosophy Forum, co-directed by myself and Janan Ismail in the philosophy department, is all about various things in different ways they define what natural philosophy is. It's what Newton called what he did. In the modern context, it's a way of doing philosophy, but it's also a way of bringing scientists and philosophers together to talk about issues of mutual interest, of which there are many, many. And so it's been a wonderful journey for us. We have various lectures, and every year the Distinguished Lecture. Anyone who wants to can get on the email list by going, if you Google Natural Philosophy Forum, it's pretty likely that you will find us. It's easy enough to get on the email list for that. And we are super excited about this year's Distinguished Lecture by Jim Peebles of Princeton University. Now, Jim is, as you'll see in a second, is a tall person. He tends to loom over you when you're talking to him, but he has also loomed over cosmology for a very long time, at least since the 1960s. He's been there for all of it. He and Robert Dicke, who was his advisor at Princeton, were part of a team to measure the relic radiation from the Big Bang, what we now call the cosmic microwave background. They had a telescope on the roof of a building at Princeton University. They were scooped by people at Bell Labs, but they were extremely gracious about being scooped, I have to say, and went on to really develop much of what we think of as the modern Big Bang cosmological model. Not only the cosmic microwave background, but galaxy formation, large-scale structure, all of the questions we still are thinking about today. In more recent years, worked on dynamical dark energy and the cosmological constant, things like that. When I was a postdoc, soon after the COBE satellite had discovered the temperature fluctuations in the cosmic microwave background, of course, this was a new thing. Everyone knew it was going to be a big deal. This is the 1990s, and everyone, all of my friends, postdocs and grad students, started working on, like, how do we deal with this? What does it mean? How do you calculate what the microwave background is telling us? How do you connect theories to observations? And multiple times, I got to hear these friends of mine, like, figure something out, and then someone would say, yes, Jim Peebles taught us that 20 years ago. And eventually, for all of this work, he was awarded the Nobel Prize in physics. And so for those of you who are philosophers, there's Nobel Prizes and there's Nobel Prizes, okay? Sometimes you do something, you make a discovery that is just so big and important that, of course, you're going to win the Nobel Prize. Other times, the Nobel Prize is awarded and people are like, oh, okay, all right, if you think that. But when Jim Peebles won the Nobel Prize, the entire cosmological community as one said, wow, that is awesome. That is wonderful. Frankly, we didn't think the Nobel Committee had it in them. But they did. And with all those accomplishments in his background, Jim is finally ready to turn to philosophy. So today he will be telling us about a physicist's homegrown philosophy of physics.
Sean, thank you, and thank you for this warm reception. I intend to try to persuade you that physicists have a philosophy that is pretty definite and clear. It's all pretty simple, with the exception of one problem, that it's very hard to find a physicist who will admit to having a philosophy. So I have to resort to observations of the way I and my colleagues in physics behave. Of course, we can ask the same question about a botanist, a geologist. Do you have a philosophy? I think the answer is yes, and it begins with a key point, which I intend to illustrate by asking you to think about an ornithologist, an expert on birds, and of the varieties of birds that exist, who has found a nondescript bird. That means a bird that's not in the official list. The ornithologist may decide to jump through all the hoops required to demonstrate that this bird is not now in the list and that it belongs in the list because here it's well described, and in the future it'll be readily identified should you find another bird of that particular sort. So you might, the ornithologist, having gone through the hoops and published and registered this bird, might well feel that, well, we have added a little to the knowledge. Knowledge of what? Well, of course, the obvious answer, knowledge of birds. But of course, there are lots of different natural sciences, each of which is making advances, all of which are contributing to knowledge. And so there is a broader question, knowledge of what? One may say it is knowledge of the natural world, but I think it's fair also to say simply that it is based on the presumption that there is a reality and that we are making contributions to discovering the nature of this reality. There's no guarantee that there is a reality, and there's no guarantee that if it exists, you can discover it. But the evidence from the practice of science certainly argues for it. In short, that in physics and in all of the natural sciences, we presume there is a reality, and that we are able to learn about the reality, learn about its nature. It's simple enough in that respect. Now, I offer an example of what goes on here, and on purpose, I wanted to mention historical remarks by Charles Sanders Peirce, if that's the way you pronounce it. Charlie, to his family, who were always worried about him, he was kind of eccentric, but he had a remarkably good way of expressing the nature of physics. Good because I agree with him. He talks about measuring the speed of sound. And one person, you understand that, well, we do learn things in society too, may investigate the velocity of sound by studying the transits of Venus and the aberration of the stars. Another by oppositions of Mars. Lots of ways to measure the speed of sound. I'll just pick one for remarks, oppositions of Mars. We need to know the distance to Mars in order to get the speed of sound, as I'll describe. At the time, people knew very well the radius of the Earth. The mariners had taught us how to find your latitude, the angular distance up from the equator or down from the equator. So go to a place where you can go up straight for 1 degree of latitude, measure the distance you traveled, and then remember that there are 360 degrees going around, so you've got the radius, the circumference of the Earth. Now, Newton's theory of gravity predicts that if you have one distance, the distance between Mars and Earth, then you can get all of the distances. Just take that for granted. An opposition of Mars happens when Mars, Earth, and the Sun are close to being in a line. Earth between Mars and Sun. At that point, Earth is as close as it's going to get to Mars. Close enough so that if you're on different places on Earth, you see the position of Mars as it moves by, passing by different stars, like a binocular. Once you have that distance from Mars, you have the distance to Jupiter. And it was known that the eclipses of moons of Jupiter, as it goes around Jupiter, these eclipses happen at times that change as Jupiter moves around and Earth moves around the Sun. So now, if you know the distance to Mars, you know the distance to Jupiter, and you know the rate at which the distance to Jupiter is changing as it moves around very slowly, we move around more rapidly. The change in distance is correlated with the change in time at which you see a moon move behind the Sun, behind Jupiter, and so you get a speed, the speed of sound. I mention this because people have been fascinated with this thing, this issue of the speed of sound for a long, long time. Here is an example of this from the earliest attempts by Romer who was measuring the time at which satellites, moons move around Jupiter. Not a very good answer, but well, in the ballpark. Then Bradley, using the effect that's very much like this, if you're standing in rain that's falling straight down and you stand still, well, you only get slightly wet on your sides. If you then walk through the rain will hit you in the front. The same with light coming from a star. And so by looking at this aberration effect, Bradley was able to infer the speed with which we're moving around the sun. Knowing the speed and, well, knowing all that, one has again, the deflection is V over C. You get V from the motion, you get C, and a number closer to reality, 3. Fizeau in France set up a mirror 8 kilometers away and had a very clever scheme for sending little flashes of light all the way to that mirror and back and timing the time it took to get there and back. You see the important point. You're doing different experiments and getting similar answers. It's what you would expect if the velocity of light had some absolute meaning. Rosa and Dorsey. At the time, we had a theory of electricity and a theory of magnetism, and a pretty good idea that electromagnetism, the combination of the two, predicts that light travels at the speed of light is electromagnetic radiation. They used that information to get a much better answer. But you notice it's in the same neighborhood as the earlier measurements. From that to Michelson, who went to Mount Wilson in Southern California, set up an observatory there to look at a mirror 20 kilometers away on another mountaintop, measured again the time for light to go there and back, and got the number, lots more digits. Michelson. Yeah, let's not go on. You noticed Essen did something very clever. He built a cavity, a cube, very precisely defined dimensions. He said, put electromagnetic radiation there that resonates, the wave moving back and forth. Knowing the dimensions and knowing the frequency of that resonance, he got again the speed of propagation of electromagnetic radiation, which is light, and an even better answer. Dumont and Cohen started collecting lots of measurements of the speed of light and got an even better answer. Cohen and Taylor, another compilation, an obscene number of digits, so many that it became impossible to decide what is the unit of length. When you say the speed of light is so many centimeters per second, what do you mean by a centimeter? Well, it used to be the distance between two scratches on a rod, on a metallic rod that was carefully housed in Paris. But there are too many digits. So in fact, it is now determined that we will define the speed of light to be the number on the bottom line and combine that with other measurements. I go through all this laborious motion to say a very simple point, but one that's really profound. The speed of light behaves as if it were an objective reality, independent of us. That if there were another civilization and they got an interest in light, and they set out to measure it, they're going to get the same answer, apart, of course, from the fact that we don't know what units they're going to use. But that the speed of light is somehow an object of reality. Just another example, electric charge. Has a shorter history, but still very substantial, and you see a sequence of measurements. The only maybe interesting thing here is to notice that between Schopper and Burge, there is a jump bigger than the measurement error. There was a crisis. Some thought that it is due to the fact that Millikan, who had developed the oil drop method, that if you took undergraduate physics, you learned about the oil drop method. His answer was off by 1% from what people using another technique, electrolysis, in which you pass a current through material, through a fluid. The current is carrying charged ions. You measure the amount of ions collected, the mass of ions collected as you pass a definite current through the system. You get an electric charge, which disagreed with Millikan by up 1%. That's still remarkably small, but still it looked like a real discrepancy. There were some who decided there's something wrong with Millikan, and indeed Millikan had the habit of discarding faulty measurements. That is a sin in a sense, except it's a sin you've got to commit. You cannot include measurements you think are faulty. If you do, you're biasing the measurement. If you don't include them, of course, you may be making a mistake because you're rejecting real measurements. So it's a delicate art to reject without biasing. It turned out, though, that the rejection of data wasn't the problem after all. It was that these drops containing little bits of charge are suspended in an electric field. They drift up or down depending on their charge and how strong the electric field is, how much it pulls on the charge of the drop, so he had to correct for the motion of the drop, which is determined by the viscosity of air, and his viscosity of air was faulty by 1%. So these are the hazards of the precise measurements, but you see we go on again until finally CODATA, unofficial source of data, has fixed on another arbitrary value that will allow you to measure other things. Again, though, the key point, this is acting as if we had aspects of reality. Why else would we get these reputable results? So, now of course, it is fair for those who question physics to ask, to what extent are you physicists influenced by your environment, by your culture? We are people and we are affected by our culture, and we try very hard to take account of that. But how do we know we're not fooling ourselves? Well, I say, although it's true that I am influenced by my culture and that I'm apt to make mistakes, therefore, nonetheless, it is very hard to question those two tables of numbers as saying, other than that, we have an aspect of reality. Now, there's another aspect to this that is mentioned by Karl Popper, a philosopher of physics, noted, I think, for saying rejection, falsifiable. People often say when they have a new theory, it has many advantages, here they are, and it's falsifiable. That's Popper. Of course, that doesn't work at all. Consider electromagnetism. We use it every day. It's well understood. It's Maxwell's equations, classical electricity and magnetism. You would never want to abandon that subject because it's so useful. But yet, if you apply it to the structure of an atom, you get the wrong answer. It means that you have falsified the theory of electromagnetism. But of course, you have, better way to put it by far is that we have a very useful approximation to electromagnetism, but we need something better. That turned out to be quantum physics. But of course, that turns out to be approximation to something else. Let's not get into that. What I like about this statement is that I see no reason to believe in Cartesian self-explanatory truisms or essential definitions. Can you do physical research by pure thought? Just to remind you, here's Descartes, after whom this is all named. Remember, I think, therefore I am. He also attempted to prove reality by starting with the assumption of a benevolent God. But of course, that's a little hard to support. Another interesting case, Ernst Mach, who I think had a wonderfully good understanding of classical physics. I remember when I taught introductory physics, I would show demonstrations taking from Ernst Mach's book, The Science of Mechanics. Requires a little explanation, but I just can't resist telling you about it. You have metallic pipe that goes down, then bends out, then goes in a circle, bends in, bends down to the little cup that contains the water running through. So you've got that, and now you pour a little water into this system, and you observe that when the water starts flowing in, and I should say, these pipes are supported by pins on top and bottom, so it's free to rotate around the axis. Okay, it's free to rotate. So you pour some water in, and you observe that the pipe starts rotating. And when the water has run through, the pipe immediately stops. It's quite dramatic. I used to love showing this to introductory physics students. You see the simple point. Angular momentum around the axis of this system is conserved to a good approximation because the pins are pretty close to frictionless. When the water is running through that outside loop, it is carrying angular momentum, like so, and it's going to have to be that the pipe is carrying angular momentum of the opposite direction. Really neat. This is physics, and it's good stuff. And I leave it as an exercise for the student to say, well, what force caused the pipes to rotate and then stop rotating? That's left as an exercise for the student. Let's proceed. Ernst Mach, as I say, had a wonderfully deep understanding of classical physics. He's mentioning here Foucault's pendulum, the law of areas, that's angular momentum. But Mach had an unfortunate fixation on avoiding metaphysics, unneeded assumptions, mystical remarks. He disliked it. Instead, it's the facts that matter. Just the facts. Don't give me those theories, just the facts. That might have been one of the reasons why people in Vienna would gather in those wonderful coffee houses in the 20s, early 30s, and discuss and try to find physics as a self-evident proposition. Surely, physics can be made self-evident, complete. Bertrand Russell encouraged that by his valiant attempts to make mathematics complete. But of course, Gödel upset that apple cart by demonstrating that if you have a mathematical system complicated enough to be interesting, there will be theorems you can't prove. Distressing indeed to mathematicians, and distressing too, I think, to the Vienna Circle, those who want to find by pure thought physics. I'm pleased to find this article by Richard Jacob Burnside. Gave us a phrase, Cartesian anxiety. If you don't have absolute truth, where are you left? What do you do? We're anchorless. But of course, that's entirely wrong. We have something to guide us, phenomenology. So, I offer one final example of this line of thinking. Albert Einstein, he wrote, "The supreme task of the physicist is to arrive at those universal elementary laws from which the cosmos can be built up by pure deduction." That's absurd. We think we have pretty good laws of physics, but we know we can't, from those laws of physics, deduce that you're here in this room. It's complicated beyond all measure. I used to think that Einstein was kidding. You know, he had a good sense of humor, and he might have been just teasing us. But no, here's another conviction, another quote. My conviction that pure mathematical construction enables us to discover the concepts and the laws that give us the key to understanding the phenomena of the universe. Well, I do not mean to take anything away from Einstein's genius, but that's just crazy. Let me, I have a very important book to present to you. Just So Stories for Small Children. You have to be a very credible young child to pay any attention to the story of how the leopard got its spots. But we have a deeply important lesson drawn from this book. Suppose a collection of very bright, very inventive, very intelligent, very persistent physicists are given a problem. We have this phenomenon, we don't understand it. Solve a problem, explain it. The odds are pretty good these inventive physicists will find a theory that accounts for the observation. And then the question becomes, is this theory at all related to the way the world really occupies itself, or is it just a just so story? How do you decide? The answer, I think, is ironclad clear. Consult the phenomena. In particular, ask whether this theory predicts anything that you didn't put into the mix to invent the theory. Can it make predictions? If it can make predictions, you can test them and ask, do the predictions agree with what you measure? If they do, that's evidence that maybe it is on the right track. Why else would this prediction agree with what's measured? And of course you could say, well, so you were lucky, a lucky accident, so make more predictions and test them. That is the big program of physics. Put another way, well, I've all said all this, isn't it? Let's go on. So philosophers and others tell us properly that there are two ways to connect theories and observations. One way is to start with a phenomenon and invent a theory to account for it. The other is to take a theory and ask, what else does it predict? If it successfully predicts something, you are encouraged to think it might be on the right track, but show me some more predictions. I showed you two examples. The speed of light, the theory is pretty simple. The speed of light, the theory is a meaningful quantity. And so you would predict that if you measure it ever better or more accurately, you'll get consistent answers. And indeed, that's observed. A simple example of the program of persuasively establishing some theories as good approximations to reality because they pass lots of predictions. The predictions pass lots of tests. Common names for these are inductive and deductive. Since I have great difficulty remembering which is which, I have just decided to invent two terms. Top down. I think of up there as all its evidence, and it comes down to you. And you find a base, a theory. Bottom up, take that theory and look for predictions. I know it's kind of an ugly notation, but well, I mean. And I come to now a couple of examples of physics that isn't physics. Hyphenated physics. I have in mind, well, so you're Italian-American, I'm a Canadian-American, although really I'm German, English, Canadian-American, but I'm American. Just keep it simple. In other words, I object for the purpose of this discussion to use the word geophysics. It's geology. It isn't physics. The Earth was assembled, we can be pretty sure, by a bunch of things clumping together, heavily dependent on the eventualities that determine what is going to be crashing in to make the Earth. You could never make a fundamental theory of the Earth out of that situation. You can't trace back to all of the eventualities that built up the Earth. In short, geology cannot be a physics because you can't make predictions, because it depends on so many too many things happen. So why do we use the term geophysics? I don't know. I'm not trying to persuade you never use the term geophysics again. I am insisting, though, that for the purpose of this theme, we shouldn't talk about geophysics. Let me try it again. Astrophysics, it's really astronomy. Biophysics, it's biology. Why did I put this? Oh, yeah, well, I like the way Max Delbruck put it. Any one cell, a human cell in a body, there are many, of course, it represents more historical and physical events because nature developed a cell through experimentation over a billion years. It must have been an immense sequence of eventualities that built things, put them together, failed, put them together another way, maybe succeeded, got something better. You cannot expect to explain a wise old bird in a few simple words. That's Delbert. Well, my addition is, or a predictive physical theory. It's not physics, simple as that. It is good, excellent science, but give it a simple name, at least for the purpose of these thoughts about the nature of physics. Hyphenated physics. Oh, well, this is hyphenated physics. I don't mean to insult you if you're a hyphenated person. We all are, after all. Only that hyphenated sciences have started to worry me. Good, that's out of the way. Emergent physics. Phil Anderson, a brilliant condensed matter physicist at Princeton. Alas, he passed away before I decided that maybe I should think about my philosophy. He wrote, and of course Phil had an axe to bear. He pointed out that experimental studies in condensed matter physics are orders of magnitude less expensive than particle physics. This was at the time, particularly, of the superconducting supercollider. The fortunes of a kingdom were being spent digging a hole down there in Ouachita, Texas, or wherever it was. He was right and wrong, of course. That particle physics has taught us so much about the nature of reality. But he emphasizes condensed matter, a superconducting system. Superconductor has properties. It is a theory. The theory of that superconductor has emerged from physics, but it is now a subject on its own, with its own skills required, its own methods of procedure, its own theories. It is an emergent theory that he would emphasize is just as intellectually interesting and challenging as any other branch of physics, and a lot less expensive than particle physics. He was right, of course, but wrong. Particle physics is also brilliant essential physics. And there is, of course, now the cautionary remark, which is really important, if I can explain it well. We know that condensed matter physics emerged from quantum physics. We even have direct evidence. Quench that superconducting material that is magnetized, and a spray of electrons appears. The electrons were there beforehand, but in a funny state. You couldn't tell where they are. They're not anywhere. They're everywhere. But that superconductor is built of electrons moving in ions. It is emergent from physics, and we see the evidence. Similarly, in biology, the study of biology is deeply important, fascinating, but it emerged from physics, pretty sure, because, well, for example, a nuclear magnetic resonance imaging experiment will reveal that you are made of atoms that are held together by the forces predicted by quantum physics. Understanding the properties, deriving the properties of a biophysical molecule from first principles is wildly impractical, but nonetheless, I think we have pretty good evidence that that biophysical molecule emerged from standard physics. The difference with standard physics is it's hard to see what it emerged from. It's hard to see eventualities creeping in. And that difference, the fact that standard physics is predictive, in some cases to remarkably high precision, is not something you can expect of biophysics or geophysics or astrophysics. So much for that. Emergent physics. Well, I've said all this. It is really fascinating. Particle theorists like to think that perhaps there is, quantum physics is emergent from something deeper. Named superstring, or string, or now M theory, lead one to think that perhaps there is a theory underlying quantum physics from which quantum physics has emerged. But it's not going to be an emergence of the sort of superconductivity from quantum physics. It's going to be a simple thing coming out of something even simpler, less capricious. And now Thomas Kuhn, who was a brilliant person, who wrote a very influential book that led many to question how solid is our physics. He's a puzzling case because he was trained as a physicist. He was an undergraduate and graduate student at Harvard University. He wrote a thesis on physics. Do I have the title there? The cohesive energy and so on. It was a real thesis published in the Physical Review. He wrote one paper with his advisor, the Nobel laureate Van Vleck. He wrote one paper on it by himself. He was well on the way to being a physicist, but he decided this was not for him. He wasn't happy. And he eventually drifted into what he often described as a historian, but I say more like a philosopher of physics, but with an unfortunate tendency to get things wrong. So I want to show you an example. Is there anything else here? Well, okay, the bottom paragraph. I'm being critical of Kuhn, and he's dead. He can't defend himself, but he was influential, and he seriously misunderstood physics, and we should note that. So this quote is too long, but what was it? There are two aspects of the negotiation, research in physics: the factual and the interpretive, experiment and theory. They're carried on concurrently. The conclusions shape the descriptions of facts just as the facts shape the conclusions drawn from them. Well, that's really interesting. Indeed, the process is circular, and what does the physical evidence have to do with it? It's circular. Now, that is very close to true, but of course is not true. And let me show you an example. You know, you didn't ever place, I have never seen a clock in this room. Any idea how fast? Oh, good. We might even finish. 1950. we had a well-developed nuclear theory, nuclear physics theory, that grew out of the bomb project, of course, but it was a lot of experiments going on that were well described by a theory in which you have neutrons, an atomic nucleus made of neutrons and protons. A free neutron can decay into a proton plus an electron. The proton is positively charged, the electron negatively charged, the neutron neutral, so charge is conserved. And you need a hypothetical particle called the neutrino, although here it's going to be called the antineutrino, to conserve energy, because it was observed that when the electron comes away on the creation of a proton, the electron doesn't have a definite energy, but there's a definite energy consumed in turning a neutron into a proton. So where did the extra energy go? Well, a hypothetical particle, the antineutrino. You know, nowadays we have a hypothetical particle, dark matter. And here, a similar crisis, a hypothetical particle, neutrino. But I should go on and point out that if the electron is inside an atom of considerable charge, a heavy element, the electron can have enough energy to force itself onto a proton to make a neutron and a neutrino. It happens. And you notice what it is a rearrangement of the entries in the top line. Let's see, take the proton plus the E minus on the right, move the antineutrino over to the neutrino, and it becomes a neutrino, not an antineutrino. And again, you see charge is conserved, and also if you give electron a lepton number +1, then the neutrino has a lepton number +1, so they're balanced. Whereas in the top line, the electron has lepton number 1, the neutrino has to have lepton number -1, so it's an antineutrino. And finally, an energetic antineutrino can hit a proton and make a neutron. The electron conserves charge, and of course it is an antilepton, so it has to be an antilepton, antineutrino, that does the job. Okay, so now, as I say, we had a well-developed nuclear physics and a hypothetical particle, and you really wanted to discover that particle. Now, it was Fred Rhinus on the right, Clyde Cohen on the left, and a group of others who decided we can detect that antineutrino. The trick is to go to a nuclear reactor. A nuclear reactor, in a nuclear reactor, there are fragile atomic nuclei like U-235. There are free neutrons floating above. A neutron may be captured by one of these fragile atomic nuclei, causing the nucleus to break apart into fragments, including neutrons. The neutrons can race around and break up other atomic nuclei and so on. If you don't stop that, you're going to have an explosion. That's why in an operating nuclear reactor, you have rods made of light elements that can have great ability to absorb neutrons that you push in to just the right place so you're controlling the reaction. So that's an operating nuclear reactor. Now, of course, many of the neutrons fail to hit an atomic nucleus. Instead, they decay. And so by decaying in the top line, there are antineutrinos produced that we interact only very weakly with ordinary matter. Most of them just freely stream out of the reactor. So this reactor is glowing, except you can't detect it, you can't see it, with antineutrinos. Neat. Build an antineutrino detector by using the bottom line. Put a lot of mass near the reactor and look for the occasional event in which an antineutrino from the reactor hits a proton, maybe in an atomic nucleus, and makes a neutron plus a positron. And a positron is very easy to detect because it'll soon hit an electron and make a couple of gamma rays. So that's the experiment, which I went into something, because a neat experiment, you had the atomic physics that predicted that if you, Rhinus and Cohen, put enough mass out there and coated it with detectors, you should be able to detect an antineutrino. Of course, if you don't detect them as predicted, that's a real crisis. We had this beautiful theory, and it's wrong. How do you rescue it? Fortunately, of course, the antineutrinos were detected. The reaction to that experiment was curious. It was welcomed, of course, but the standard and firm thinking was, of course they would detect antineutrinos. Our theory is too good. That's bad physics at the time. It was, at last, it took, what was it, 40 years for the accomplishment to be recognized with a powerful step forward it was for Linus to be awarded the Nobel Prize in Physics. Anything else to say? No. Notice that this experiment was designed according to the theory, and the theory was derived from similar experiments. It's circular, except no, it's not. It's critical. It's critical. Either you detect those predicted antineutrinos or you don't, and the answers will greatly affect the course of development of physics. Oh, well, okay, so we're done with that. Linus's reward on the Nobel Prize. 1995. They were doing this in the early 1950s, but Linus was a cheerful person. I suppose he was sure someday it would be recognized, and it was at last. Kuhn. Oh, yeah. Kuhn, Thomas Kuhn, knew that experiment. He wrote about it. The gigantic scintillation counter is designed to demonstrate the existence of the neutrino. He knew that experiment, yet somehow he totally messed up the point. I hope he is no longer with us. I'm embarrassed to be criticizing someone who cannot defend themselves. But really, if you're a fan of Thomas Kuhn, I ask you, please, reconsider. He was trained as a physicist. Why didn't he recognize what a magnificent accomplishment it was? Okay, the expanding universe. Well, here's Einstein. By pure thought, close to it, inventing a new theory of gravitation, general relativity, and saying this theory works best in a universe that is the same everywhere. He was in communication with the Dutch astronomer Willem de Sitter. De Sitter was a very intelligent, clever mathematician, physicist, as well as astronomer. De Sitter was very blunt with Einstein. Einstein, you're crazy. The galaxies around us are distributed in a distinctly clumpy way. I see no evidence of your homogeneous universe. He was blunt. Einstein was serene. I'm not sure he even understood what de Sitter was saying, but okay. So here is this is Professor Dr. Willem de Sitter, director of the Leiden Observatory, an esteemed figure. And here a colleague has made a cartoon. The lambda shape, which is backwards, but I'll come to in a moment. And imagine that we live in a universe with 2 dimensions in space, not 3, 2 dimensions. You live on the surface of that balloon. You must not ask what's off the surface. You don't live there. You live on the balloon. Okay? So live with it. Here is the artist's impression of a bunch of galaxies. Imagine someone is blowing up the balloon. We have to be careful. The galaxies are not expanding. So far as we can tell, our galaxy, the physics on our galaxy would be the same if there were no other galaxies. There is a whole host of other galaxies. Deep puzzle, why do we need them? Who ordered all those other galaxies? Never mind. The galaxies are not expanding. You're not expanding, except maybe biological effects. But if you sit on one galaxy, you will notice that the other galaxies are moving away from you, as if the universe was expanding away from you. You are the center of expansion of the universe. But you notice everybody sees that same effect. Everybody sees the other galaxies moving away from them. That's the expanding universe. Good. We're under, that's under control. So Sean mentioned that the space is filled with a sea of radiation, microwave radiation, wavelengths on the order of centimeters. It's a very smooth sea, disturbed, of course, by the presence of matter, like lumps of matter like us, but to a very small degree. A smooth sea of radiation. That sea of radiation has an energy spectrum, that is to say, intensity at each wavelength, as shown here. The spectrum is that of a black body, or a statistical relaxation. Take a container, put some radiation in it, put a few atoms in it that can cause the radiation photons to be absorbed and re-emitted, or to be redshifted or blue shifted, and let it relax to statistical equilibrium. The intensity at each wavelength is predicted to depend on only one parameter, the temperature, and the intensity as a function of wavelength or frequency at the bottom. The predicted line is there somewhere. It is spectacularly close to thermal statistical equilibrium. That is not about to happen in the universe as it is now. It's transparent to this radiation. Nothing to cause it to relax to statistical thermal equilibrium, yet it has. The easy explanation, it's because the universe is expanding. It was at one time very hot and very dense, and forced relaxation to statistical thermal equilibrium. As the universe expanded, the density dropped, the radiation didn't go away. There's no place for it to go. The universe is the same everywhere, but the expansion cooled it and left us with this remarkably good approximation to thermal radiation. Now, I've brought along an experimental demonstration of something that used to please me when I was a kid and still pleases me. Isn't that marvelous? It always works. I love it. And why the difference in tone? Well, half weight here is longer than half weight here. It's a resonance effect set up by boundary conditions, and the universe. I have it already. Yeah. In the early universe, it was very hot. Temperature was so high that radiation drove all the electrons off the ions. So the electrons strongly scattered the radiation. The electrons were strongly scattered by the ions. The result is that radiation, electrons, and ions acted like a fluid. And like that's this fluid, the air, and like the boundary conditions that are set here by the size of the container, in the early universe, the boundary conditions are set by the event at a redshift when the universe was about 1,000th its present dimension, the temperature 1,000 times its present value, around 3,000 Kelvin. The electrons were able to combine onto the ions. The atoms don't interact much with radiation, and so this fluid was broken apart into free-streaming radiation and atoms, neutral atoms. But the boundary condition that this happened rather abruptly gave us oscillations that were frozen in to the pattern shown here. In the upper diagram, this is, well, it's the, if you like the terms, it's the analog of a Fourier transform. It's a spherical harmonic transform. Never mind. we have a theory shown by the blue line. We have measurements to exquisite precision that look just like the theory. The same effect is observed in galaxies. Galaxies are far fewer than photons in the sea of thermal radiation, but you can find the same oscillatory behavior. The same theory gives you the solid black curve down below and the blue curve up above. It's exquisitely measured. Here is an exquisitely well-defined phenomenon. The shapes of those oscillations depend on a number of parameters. Just as in this demonstration, you needed to analyze it, you needed to know the speed of sound. You need to know the speed of sound in that mixture of matter and radiation up to redshift of 1,000, expansion factor of 1,000, and other things are needed. The result is that one is able to infer the values of some physical parameters. The expansion of the universe is written as V equals HR. H is Hubble's constant. It can be inferred by two methods. The top three, using observations of this pattern, exquisitely measured to get the fit just right. You need a certain value of the Hubble constant. You can also measure it directly, as is being done here in Johns Hopkins and elsewhere. We have two measurements. The first, on the fourth line, is inconsistent with what you get from the theory of oscillations. The bottom line is consistent with what you get from the theory of oscillations. An interesting situation, there may be an anomaly. If there's an anomaly, it's big news because it will tell us that our present theory isn't quite right. But if it's not an anomaly, well, then it's not an anomaly. Our theory is better than we had feared. Now, what's really important to emphasize is that you have other examples. For example, the baryon density. We have baryons, that's protons and neutrons. We're made of baryons. The baryon mass density in units we need not bother with, but it can be measured locally, as in the bottom line, from fast radio bursts. That radiation from pulses of radio radiation traveling us from distant galaxies are delayed by the plasma between the galaxies. That delay depends on the amount of baryons. We get a baryon density, never mind the units. Fitting to these oscillations up to a redshift of 1,000 gives you another answer. And the evidence is that the helium that is so very abundant in our universe now was produced in the early universe. You go through all of that theory, you get yet another answer. 3 different ways to measure the baryon density. They more or less agree. And that's covering a considerable range of the past history of the universe. And finally, you can go through the mass density, but I'm getting, let's move on. We're not too much detail. Well, let's go on. Now we have an interesting situation. I've described in some detail the fact that we have a very well-established, well-tested quantum theory of small-scale physics. Tested thoroughly, now with many applications, maybe not yet quantum computers, but quantum physics is used endlessly. It works time and time again. It is a very successful theory. We have general relativity that gave us the expanding universe. In those tests I mentioned, as well as many others, that are equally well persuasively established evidence that we have a good theory of large-scale physics. And then we have the slight problem that the two theories are not consistent. What do we do? I've been talking too much. Two physics peacefully coexist. We have two physics, they peacefully coexist. You can either look on small scales or small. Either way, you have a theory. Why are you complaining? Well, the problem is it's not the same theory. And I don't think I'll go into, let's go on. Eugene P. Wigner, a deeply thoughtful, brilliant theorist, was willing to write the two theories could not be united, no mathematical formulation exists to which both of these theories are approximations. All physicists believe a union of the two theories is inherently possible and will be found. Nevertheless, it is also possible to imagine that no union exists between the two physics. That is really a brave remark. We are conditioned to think there is one reality. Do we have to live with two? Nah, there's got to be a way out. But Wigner was right. We don't know there's a way out. And so I draw your attention to C.P. Snow, who you might remember wrote on two cultures, the literary and the scientific, where he would put mathematics with the scientific part. And he remarked on Hardy, a truly brilliant mathematician, the one who invited the spectacularly, intuitively capable Indian mathematician Ramanujan to Cambridge, where Ramanujan suffered horribly from the weather. A friend once saw him lying on his bed in all his clothing, very uncomfortable. He didn't understand the use of sheets. He was a convinced vegetarian. You don't eat meat. Hardy is saying you need some good, strong British beef. It was horrible. Hardy should have gone to India to visit Ramanujan. Anyway, Hardy was a brilliant physicist, inspired many. He said, what is it now? Have you noticed how the word intellectual is used nowadays? There seems to be a new definition, which certainly doesn't include Rutherford or Eddington or Dirac or Adrian and me, or me. Adrian, I am told, is shorthand for people like those other people. It's hard to imagine people looking down on the accomplishments of these three people. Rutherford, brilliant experimentalist, gave us the atom. Eddington, among the first to recognize that Einstein's general relativity is really interesting. Brilliant book on stellar structure. Dirac, spectacular. He created the beautiful notation of quantum physics. He created quantum field theory. How could you look down on such a person? But of course, I'm not looking down from the point of view of a literary academician. But I'm betting, that liberal arts people have similar thoughts that Hardy and those famous physicists look down on us. I'm very sure Rutherford, who freely expressed his contempt over stamp collectors and other branches of physics that he didn't approve of, surely did. What's the lesson? For society and for our problem with two physics. I would like to say it's a problem for the student, but in fact it is. If this problem is going to be solved, it won't be by me. It'll be someone flexible, And I wonder if it'll be someone who is capable of thinking in that vast gap between the literary subjects and the physical subjects. Well, a problem for the student, and quite lots of luck with it. Thank you very much.
Thanks, Jim. We have time for a few questions. I'm going to bring you the microphone. You're going to speak into it.
Well, so thank you very much for that really inspiring talk. So you emphasized the importance of the interplay between experiment and theory, and in particular, prediction, the importance of prediction.
Right.
AI models do a pretty good job of making predictions. AI models, artificial intelligence models, can do a pretty good job of, for example, predicting the motion of the planets and things like that. How does that fit into the story?
If AI is using physical theory to predict the motions of the planets, then it hasn't really made a prediction. It has checked a prediction, checked a theory. Can AI invent a new concept? We recall that AI is taught by reading everything that's ever written. That means that it is very adept at taking written thoughts and stringing them together. Can it create a new thought? What does that gesture mean? I have no idea where AI is going. I don't think any of us can anticipate what's going to come of it. But I was charmed to read a little essay that said, you know, the invention of the bicycle upset the horse and buggy state no end. What's to become of the world if we don't support the horses and buggies? These people are all zipping around on their bicycles. But then we learn to live with bicycles. So how will it turn out? I have no idea.
All right, another question?
Jim, when you describe the interplay between theory and measurement, I mean, it's just as we describe it in physics. We have theory, it has to conform to measurement. It's a very simple process. But in the real world of physics, as you know, it's often more complicated. We get measurements, we don't understand them. We say, maybe they're not right. Maybe we should hold on to the theory. And so my question is, are physicists really physicists when we look at measurements in theory, or are we philosophers?
One thing for sure, we're people with all of the frailties and brilliance of people. We have the Hubble tension. We have two well-experienced, very careful groups getting answers that disagree. What can the rest of us do? We stand back and watch the fight. Of course we will make irrational decisions. My favorite irrational decision is that people, until 1960, the empirical tests of general relativity were scant, practically non-existent. Yet that theory is in the wonderful series of theoretical books on physics, Volume 2, Relativistic Classical Field Theories. The first two-thirds, electromagnetism, perfectly logical, it's used all the time. The last third, general relativity, which has had practically no evidence. That's quite irrational, but people are not rational. Instead, you make judgments. And how do we handle the fact that we're making judgments? I think by compulsively repeating experiments, repeating analyses, repeating all the arguments, and eventually maybe getting them right. It can be done.
More questions? Can't see anything. Yeah? No? Oh, right there. Oh, two of them. Okay, good.
Hi, thank you for the talk. This might sound like a caricature, so I'm asking for clarification, but it seemed like the primary objection to Kuhn was that he wasn't understanding what could happen if this anti-neutrino experiment went wrong. Is Kuhn just saying that science can at best be circular? And it seemed like maybe you were pointing out that no, science can also be wrong. Is Kuhn right to say that science can at best be circular if we add that asterisk?
So you make a very good point. I gave you one example, and one example surely does not destroy a reputation. But this fall, there will appear a book, modestly priced, by me, in which I give several more examples.
All right, one last question.
So to your point of this idea of nomenclature of what should this hyphenated physics, and should there be or not be such things, and the argument you gave was measurements to a high degree of precision, right? That we can predict the speed of light from multiple different angles to a high precision, and that's why it's physics.
Yes.
But other hyphenated physics cannot do that. But shouldn't precision be something that depends on the theory and the phenomenology that we're trying to describe? So
Well, it
a prediction in
certainly
biophysics doesn't have to be precise up to like 5 decimal points.
No, it doesn't have to be precise. And of course, there is no measurement that does not have an uncertainty if you distinguish counting eggs in a basket. Apart from that, any interesting measurement has an uncertainty that you have to live with that. And so when you make a judgment call, is this theory predicted, supported by your measurement or not? Is the prediction successfully confirmed? There's always has to be a judgment call. We have to live with that. And because we are people, and people are not totally rational and are affected by many outside influences, you have to worry, are you being objective in making this decision you make? That's part of life, all of life, but it's certainly part of physics. And how do you handle that? You pile case upon case. Repetitive. It gets tedious to start reading all of the tests that you can find in a book that will appear next fall. It's very important to say we don't know anything absolutely true about the world.
I think we know something absolutely true. This is a fantastic choice for our fourth distinguished lecturer at the Natural Philosophy Forum.